Hello everyone, my name's Dr. Vile. Welcome to my YouTube channel for A-Level Chemistry. If you find these videos helpful, please like them, please subscribe, please keep checking back for more content which will be added regularly. The purpose of this video is going to be focusing in on one of the mechanisms that you need to know for organic chemistry. It's an AS mechanism on the WJEC syllabus, and it's going to be focusing on electrophilic addition, looking at alkenes. So let's start off by looking at what we mean by this. It's a nice simple alkene. So an alkene has this carbon-to-carbon double bond. Let's just go with ethene because it's nice and simple. And if you react ethene with, let's just say, X bonded to Y, we'll look at what X and Y can be over the subsequent slides. But what happens is the double bond breaks, and then you form a new bond to X at one of the carbons, a new bond to Y. I'm drawing this dreadfully, let me rub that out. That is, you've got your bond to X on one of the carbons and your bond to Y on the other carbon, and then you've got your hydrogens here. So hopefully you can see why this is an addition reaction, because we're adding X and Y across the double bond, forming a single bond and forming new bonds to X and Y. Notice that X adds to one carbon and Y adds to the other carbon, and we'll see why when we look at the mechanism. So what we're going to do on the next slide is, rather than dealing with X and Y, we're going to make it specific, and we'll look at the reaction of ethene with bromine to see how this happens. So here's ethene. And then bromine is Br2. So bromine bonded to bromine via a covalent bond. Now it's worth noting that as the bromine molecule approaches the pi bond in ethene, the electrons in the bromine molecule become polarized, so it pushes electrons towards one of the bromines. That makes this bromine here delta negative because the electrons move that way, and this bromine becomes delta positive. So we create what we call an induced dipole, which is a dipole that's kind of made by the repulsion of the electrons. And in terms of how this reaction proceeds, this pi bond here, the double bond, is very electron rich, so it's very negatively charged. And the pi bond is attracted to the delta positive bromine. So we have a curly arrow here going from the pi bond to the bromine. This is a bond forming curly arrow. So we're going to get a new carbon to bromine bond formed. And then this bond here breaks and both of the electrons move onto the other bromine. So we've got two curly arrows. One is a bond forming curly arrow from carbon to bromine, and then your bromine to bromine bond breaks with the electrons moving on to the other bromine. And what is made as a consequence is that you now have a carbon to carbon single bond, because we've used some of the electrons to make this carbon to bromine bond. You've got a new carbon to bromine bond here, and then you've got your hydrogens that were bonded originally. But because we've used some of the electrons from the pi bond to make this new carbon to bromine bond, what this does is makes this carbon positive. So we've created what we call a carbocation, a carbon with a positive charge. And we've also got a bromine, Br, that has now gained a pair of electrons, so it is Br minus. And then in the final step, we add another curly arrow that shows a bond forming between the Br minus and the carbocation. So your curly arrow starts at the Br minus. Remember, curly arrows always go from negative to positive. And what we've done is we formed this new carbon to bromine bond. And the product, if we were looking at how we name this, is 1,2-dibromo ethane. So why is it called that? Well, it's ethane because there's two carbons. Dibromo means two bromines. And we have to specify where the bromines are because they could be on the same carbon. But in this case, they're on different carbons. So we call this 1,2-dibromo ethane. And hopefully you can see why this is addition, because we're adding the bromine across the double bond, and it's electrophilic addition. This Br here, if I get the highlighter pen out, this Br with the delta plus is effectively acting as an electrophile, where an electrophile is something that is electron deficient and wants electrons, and it gets them from the pi bond. So this is our electrophile and it's addition, so it's electrophilic addition. We're going to see a very similar mechanism when we look at electrophilic substitution when we look at benzene in a separate video. Anyway, what I want to do on the next one now, the final one, is show you this mechanism but applied to a more complicated problem. So it's really important that you understand the curly arrows on this slide before you go any further, because we're going to look at what happens if we have an unsymmetrical alkene like propene, and we're going to react it with hydrogen bromide instead. So let's have a look at that. So propene. Propene has got 3 carbons, 1, 2, 3. Double bond between 2 of them, and then stick your hydrogens on. And it's the reaction of propene with hydrogen bromide. So here's our hydrogen bromide, HBr. Now the big difference is hydrogen bromide is already a polar molecule, unlike bromine, which had that induced dipole, but the hydrogen is going to be delta plus, and the bromine is going to be delta negative, delta minus. So the curly arrows at first start from the same place. So from the pi bond between the carbons to the delta positive hydrogen here, so forming a new carbon to hydrogen bond, and then this hydrogen to bromine bond breaks. Oh, that's messy. The hydrogen to bromine bond breaks and both of the electrons move on to the bromine. So it looks pretty similar so far. However, what forms as a consequence is 2 different things, and I'm going to show you why. You've got your 3 carbons, 1, 2, 3. But the question is, where do we put the carbocation? You could put your carbocation in the middle, like so. And the hydrogen adds on to the end carbon. That is one of the possibilities. The other possibility is that the carbocation goes on the end, like this, and then you have your hydrogens. So these are your 2 possibilities. And you probably are sat there wondering, well, which one is it? And the answer is it's both, but not in equal amounts. So the actual answer is that you get more of this one and less of this one. And you might still be wondering, well, why does that happen? Well, it happens due to something called the inductive effect. In both of these intermediates, you get a carbocation formed, which is a carbon with a positive charge on it. So the question is, which is the most stable carbocation? Well, it has to be this one, where it's the one in the middle. And the reason is, this is what we call a secondary carbocation. These CH3 groups either side of it are pushing electrons towards this carbocation, which stabilizes it. So you've got the inductive effect happening like this in two different directions, where it's pushing electrons towards this carbocation. Whereas on this one on the right, you've only got the inductive effect happening in one direction. It's what we call a primary carbocation. And that means that this is less stable. And if it's less stable, you get less of it formed. So, as I say, the answer is that both of these form, but there's more of one than the other. So you can picture now you've got your little pot where this reaction is taking place, and you have both of these, more of the left-hand side one than the right-hand side one. But you've also got your Br minus that was formed from the previous step. And the reality then is that the Br minus can attack here, and it attacks here, and what you end up is a mixture of products. The first one is shown here, 2-bromopropane. Now 2-bromopropane is your major product, so there is more of this. And the alternative product, the byproduct, is 1-bromopropane. So you've still got your free carbons, but what you find is the carbon to bromine bond is at the end of the chain. And then you add on your other hydrogens, but this is the minor product. And it all comes down to the stability of the carbocation in the middle. And this particular mechanism applies when we're dealing with unsymmetrical alkenes reacting with hydrogen bromide. Anyway, I hope that was helpful. If you did find it helpful, please like, please subscribe, please keep checking back for other content, and I will see you next time. Thank you very much.